Thank you, Massimo. Thank you also to Vanderlei. Wouldn't be here without Vanderlei, and appreciate his efforts to make this happen. And to His Excellency Cardinal Kirkson, who apparently is not here, so I will pass that on to him personally. So I'm going to be talking about a subject that in this session on quantum simulation with ultra-cold atoms. And the idea is that we have, instead of a digital computer to simulate a model, which in turn simulates a material, let's say some kind of electronic material, for example, a superconductor. Instead of the digital computer, we could replace that digital computer with a dedicated apparatus that is designed to solve precisely that model. So then there's no question that the model is what we think it is because we built it. So it's not necessarily a model of a particular material, and this is something that has to be discussed seriously. If you're solving a model, the model may or may not be an adequate model of the material that you are simulating. So keeping that in mind, this is like a way of solving a Hamiltonian and a computer, but in a real apparatus. So in that sense, it's been called analog quantum simulation. All right, so should advance, yeah. So here are a number of, down the lower left, parameters that may be tuned in some particular way, interactions via Feshbach resonance. And the interactions are highly tunable. The Feshbach resonances in many atoms, many elements are tunable. And it gives us an immense ability to do things that we wouldn't be able to do in a real material. Lattice hopping, all the lattice parameters, temperature, density, dimensionality. So this picture in the middle, in the lower middle section, are optical lattice configurations. So one can make potentials using laser beams, and a good example of that is a standing wave, in which we just retroreflect two laser beams and they form a periodic array. And in that sense, that's the one in the lower left, the 1D geometry, the one-dimensional optical lattice. In that sense, we make a periodic potential. So there's many examples that people are looking at right now: quantum magnetism, exotic superconductivity, strongly interacting 1D systems. And the first and the third are topics that I'll discuss here: quantum criticality, disordered insulators, topological materials, et cetera. And there's just an incredible number of things that we can vary in order to, in the pursuit of the realization of this particular model. So here's an example going back to 2002. This will be familiar to many of you in this audience who work in cold atoms. I think I would safe to say all of us who work in cold atoms will know what this experiment is. This is really, this is Emmanuel Bloch's experiment, which really put quantum simulation of this kind on the roadmap. And so what it is an optical standing wave in 3 dimensions that forms an insulator, but it's a particular type of an insulator. It's a Mott insulator in which it's interaction driven. So the interactions are sufficiently repulsive. The atoms even themselves out. So if there's a density of average density of 1 per site, it'll be exactly 1 per site. And this is really, I think, the first example of a non-trivial many-body state in cold atoms. It was suggested that cold atoms would be a excellent platform to do this by Peter Zoller and his group a few years prior to the realization. There's a number of review articles on this topic, and I've indicated a few of them. And I have to be careful of my colleagues, but if I've forgotten any of you, my apologies. But that's guaranteed to be a few of them there. And I know most of these people are here at this meeting. All right, so we've then moved on from the Bose-Hubbard model to Fermi-Hubbard model. The fermions are very interesting because the fermionic atoms can be stand-ins for the electrons in a real material. And so you can make a pseudo-spin-a-half system and populate an optical lattice and then make measurements. So this is the Fermi-Hubbard model. It's a very simple model to write down, but it suffers from what's called the sign problem, and it can't be solved in digital computers for any doping that's away from one atom per site. So this is the kinetic energy term, which is the hopping from one site to another. This is the interaction term. And the interaction term is what, again, drives it to be a Mott insulator. But the Mott insulator for the fermionic atoms with positive U is a antiferromagnet. So, and we're considering just single band. So this is, as I said, is really become a paradigm model of correlated matter. It's been proposed model for high temperature superconductors, which we don't know exactly whether this model is a good representation of the high temperature superconductors, but it well could be. So this is a phase diagram, kind of a generic high TC material. There's antiferromagnetic order in green on the left, some strange metal pseudogap regime in the middle, above a superconducting dome. And we don't know for sure whether the Hubbard model entails this D-wave superconductor. But this is one of the goals of our community, is to find out whether the model actually does solve for, does contain superconductivity. So this is our experiment from a few years ago. This is back in 2015. This is about 10 to the 5th lithium atoms that are in a 3-dimensional optical lattice. So this is a cubic configuration, simple cubic lattice. And we can measure the antiferromagnetic order that exists by doing Bragg scattering of light. This is very similar to what our condensed matter colleagues do with scattering neutrons. It's a spin-sensitive technique. So by shining the light at a particular angle, the Bragg angle, and detecting the diffracted light at the Bragg angle on the other side, one can measure the correlations in this system. So the data here on the left, this is a structure factor, which is a measure of the correlations of the gas antiferromagnetic order as a function of interaction strength U. And on the right is that same data, but compared with theory. The theory comes from Teresa Paiva, Ehsan Katami, and Richard Skolatar, and Nandini Trivedi, and David Hughes. Kind of an all-star lineup in our theory collaboration. So the temperature turns out to fit something which is just above the nail temperature. The nail temperature is believed to be about 0.37 in units of the hopping, and we got to about 0.5. So this indicates that there are antiferromagnetic correlations that are already there and developing, but it it's not below the phase transition where most of the spins are in this adiabatic or in the regime of quantum magnetism. So this problem has since been, people have taken it much further. There are now experiments with 2D quantum microscope in which you can measure the spin and position of single atoms. It's really an amazing accomplishment. And groups such as Marcus Greiner's group, Emmanuel Bloch's group, Martin Zwierlein, Wasim Bakker, amongst others, have realized these two-dimensional quantum microscopes. So let me just acknowledge the people here. I'm not going to read all their names, but these are the group of people who are involved, the ones shown in red, with this particular experiment. Now let me move on to talking about one-dimensional physics. So the excitations in 1D are very different than excitations in 3D. So in 1D, electrons can move to the left or the right, but they can't go over another electron. And so any excitation that gets, thank you, any excitation which is excited somewhere along this line is propagated down the line. And that's very different than in 3D, where there's quasi-particle-like excitations, there's single particle-like and fermionic. And that's the basis of the mean field picture, or the Landau Fermi liquid picture of excitations in 3D systems. So the 1D system is this Tominaga-Ledinger liquid is like the bosonic Hubbard model in the sense that it's a kind of a searchlight problem is very fundamental in one-dimensional physics. So particle hole excitations are different in the Landau Fermi liquid theory than they are in the Yang-Godin or Tominaga-Ledinger liquid theory, in the sense that you have excitations that are just around the Fermi energy, and they have to go from the Fermi surface is just 2 points, a low momentum and a high momentum point. So there are two excitations that people have identified on the Ledinger liquid theory. One is a charge or density excitation, and one is a spin excitation. So the two turn out completely separate from one another, which is really quite amazing. And they have different velocities. So they're predicted, the spin part of the electron and the charge part of the electron are predicted to move more slowly from one, or different velocities from one another. And with the spin mode being slow and the charge mode being fast. So that's a remarkable property when you think about it a little bit, with the electrons in the electron spin moving away from the electron charge. So this is a phenomena that's been seen before in condensed matter physics. There are a number of realizations. A few of them have been shown here. In cold atoms, Peter Zoller and his group, Alicio Riccati are the principal authors in this work. And they had ideas on how to see this spin charge separation in cold atoms back in 2003. And Alessio happened to be visiting my lab at that period of time. And I got interested in the problem from talking with him about this work. There's something else called Bragg spectroscopy, which turns out to be a more quantitative technique. The Bragg spectroscopy of this problem, we first need to make a one-dimensional geometry. We do that with a two-dimensional optical lattice, which produces a bundle of one-dimensional tubes. And so we fill those tubes up with atoms on the order of 100 atoms. And the Bragg spectroscopy entails having two laser beams impingent on this one-dimensional tube at a slight angle, in our case about 5 degrees, which imparts momentum, and then the two laser beams have slightly different energies. So there's charge density wave, which can be excited independently of the spin density wave, and I'm getting the chairman starting to look a little nervous. I better speed up. So the charge density wave can be excited with a symmetric excitation, and the spin density wave is an anti-symmetric. This is from his group, from Massimo's group a number of years ago now. In 2014, and Guido Pagano, the first author of this paper, is now a faculty member in our department. So things come around, and Guido and Massimo and Leonardo Filani measured what's called the structure factor for a one-dimensional gas of fermions, but only the charge degree of freedom. And for technical reasons, we did the same experiment and also just for the charge wave and not for the spin density wave. It turns out the spin density wave is challenging from a technical perspective. We figured out how to deal with that, and I'll talk about that in a moment. This was also a pioneering experiment by Emmanuel Bloch again and his group, in which they selectively remove a single atom, and by removing a single atom, they produce a large energy that causes excitations of both the spin density wave and the charge density wave, and they could see that they move at different speeds. It's not in the Luttinger liquid regime, it's a higher energy excitation, but nonetheless it is spin charge separation. So this is our data, and you can see that there's a splitting between the spin and the charge velocities, which is governed by that location of the peak as a function of the peak of the distribution as a function of interaction strength. In the blue are the spin degrees of freedom, in the red are the charge. There's only two free parameters in a simulation of the simulation, a digital simulation using something called beta ansatz, and that those two free parameters are temperature, overall scale factor, and the theory agrees extraordinarily well, and this is before we've added nonlinear corrections, in which case it agrees almost perfectly. So this now is a way of showing spin charge separation in a very quantitative way. Never been seen before in a way which could be compared with theory. And so until something, you needed to control the excitations and make sure that they're in under the right conditions. So you can see as a function of interaction strength, the velocity here, which is plotted for the spin degree of freedom in blue, or the red is the charge degree of freedom in red. And let me acknowledge the people who did this: Danielle Cavazos, Ruin Senaratny, and this reads like a UN register, Ashish Kafle. All right, thank you.